Hello, my name is Meng Ling, a graduate student from computer science at the Ohio State University. With my co-authors, we're going to present our paper, Document Domain Randomization for Deep Learning Document Layout Extraction. It's about preparing training data for document layout extraction using convolutional neural networks automatically and requiring no human annotation. We are in an era with exploding number of scholarly publications, and recognizing the layout of this mostly unstructured digital form, especially those blurry scanned pages or those that do not follow format guidelines, is crucial in downstream document understanding tasks, whether it is table figure analysis or semantic analysis of texts. Document layout extraction by deep learning methods using CNNs have become so powerful and dominant these days. CNNs convert the extraction task to a task of image segmentation and recognition. The CNN method for such a task is mostly supervised learning, which requires a large number of annotated training data. The accuracy of the training data and its consistency with the target domain therefore determine the quality of the trained model and the accuracy of the predictions. Carefully annotated data, however, are difficult to obtain, especially for those automatically generating training data that effectively mimic those of the target domain. Our goal is to develop a method that can generate training data that is 100% accurate without human labeling. Also, we want the generated data to be as close to the target domain as possible through randomization, so as to minimize the discrepancy between the train and test sets. Almost all existing solutions attempt to produce high-fidelity realistic pages with the correct semantics and figures, typically by annotating existing publications using methods such as crowdsourcing, smart annotation, and the decoding of markup languages such as XML and LaTeX. Our solution graphically renders pseudo-pages by varying page appearances and semantic content to generate the target domain surrogates. We call this method Document Domain Randomization, or DDR, which is similar to document randomization to domain randomization in robotics and computer vision. DDR can be considered the synthesizing method, but is different from most existing synthesizing methods. For example, some methods collect original high-fidelity document elements by web scraping or manual labeling with rendered tables occasionally. Then they synthesize them randomly on a page or replace text blocks by figures and tables. A recent approach called deep paper composure uses a rendering solution and they randomize figure table positions among pseudo texts following specific document formats. Our work in DDR broadens this approach by randomizing many document features to acquire and diversify both structural and semantic labels. It had the advantage of producing millions of training samples rapidly, with accurate ground truths and without the need for human annotation. Now, let's look at the details of DDR. Given a document, our goal with DDR is to accurately recognize document parts by making examples available at the training stage by diversifying a distinct set of appearance variables. Title, length, height, distance to other components. Abstract location, style, and format. Text in paragraph, section titles, and the captions. Non-textual components, number per page, position relative to text and columns. Existence of caption position and caption tags, page margins, column widths, and the distances. In summary, we randomize three key aspects of our document. First, font, style, and size in textual components, which we learn from style guides and from observations on the deviations. Two, non-textual components such as figure, tables, equations, and so on. It is common to use existing collections or to create new ones by rendering, as long as they are diverse enough. Three, the spatial relationships between these components, which can also be measured or estimated. Our render-to-real workflow uses a two-step procedure. Step 1, we create the semantic textual and non-textual content. Step 2, we randomize the visual look of the paper and render the pseudo pages. For non-textual content, including algorithms, figures, tables, and equations, we rely on the VIZ30K dataset, which covers 30 years of IEEE Viz conference publications and is a collection of both modern high-quality digital prints and low-quality scans of document pages. Textual content, including title, abstract, section headings, captions, and body text, are randomized yet meaningful text generated by the Sedlmair method. In step 2, we vary the locations of the textual and non-textual components on a target-adjusted page, vary distances between document components, and use a target-adjusted font style and size. In the examples of this study, we incorporated text font styles and sizes from the ACL and the Viz target domains. As the pages are generated, ground truth information are automatically recorded. Finally, we can generate any number of training samples with 100% accurate labels and bounding boxes in any predefined randomization style. Now let's look at a few examples of the generated pages. The colored rectangles on the page are bounding boxes with different colors representing different label types. This page has authors with affiliations, a single column abstract in italics with a line of keywords, and subsection titles numbered and aligned to the middle. This page has a teaser image with caption text in bold below it, a wide abstract, and body text randomly broken into paragraphs. This is an inner page with an equation on the upper left, an algorithm on the lower left, a table on the upper right with caption above it. This enlarged view shows the caption of a figure and a part of the body text. If you read them, you'll see that the text is random yet semantically meaningful. Will the DDR method work and how will it behave? We hypothesize that, performance-wise, DDR can achieve competitive results and that target domain adapted DDR training data will lead to better test performance. In terms of sensitivity, will CNN model's performance be adversely affected by reduced samples and increased labeling noise in DDR data, just like other deep learning methods? We conduct empirical experiments to test this hypothesis accordingly. First, we benchmark and compare DDR-based training data on a tested dataset. Second, we conduct experiments where the train and test styles may or may not match. Then, we evaluate CNN model's performance by reducing trained sample size and varying the error rates in label types in a reasonable range. Finally, we examine model prediction errors to understand what caused those errors and how to correct them. We use the following setups in the evaluation experiments. We focus on specific two-column body text format that is common in scholarly articles. We selected 3 datasets for style input and testing. CS150 is a well-known computer science dataset containing 150 computer science conference papers. Here, CS150X is a part of CS150 having two-column text format. ACL300 consists of 300 double-column papers randomly chosen from ACL Anthology. ACL300 is a dataset we predicted and curated. The other is VIZ300, roughly 300 papers, or a 10% portion of the IEEE Viz dataset mentioned earlier. In our experiment, we used fast RSAing for training and prediction, as it showed a good localization in our pilot studies. The inputs are image of DDR-generated paper pages, output label, types, and bounding boxes. For each experiment, we generated 23K training pages. To measure prediction performance on the tested dataset, we used accuracy, recall, F1 score, and the mean average precision, or MAP. In the first experiment, we generated CS150X style training data using DDR and tested on the CS150X dataset. We compared the prediction accuracy on 2 document classes, figures and tables, to be consistent with other studies. This table shows the evaluation results for localizing figures and tables. Please note these studies are not exactly the same because they tested on different subsets of the dataset. We highlighted our results in both for easy comparison. Our results are comparable to Clark and the Diwala's results from PDF figures and are better than the others. Our method had a slight lower precision, but increased recall for both figure and table detection. Our F1 score for table detection is higher and remains competitive for figure detection. This result supports the hypothesis that our DDR approach can achieve competitive performance. In the second experiment, we evaluated prediction accuracy when the train and the test datasets align and do not align. We have three train styles, based on ACL and V's, based on ACL only, and based on V's only, and the two test styles, ACL and V's. This yields 6 train test pairs, and we tested for all 9 classes. This figure shows the average results in MAP and IOU of 0.8 for the 9 label classes. Solid lines are for the ACL test set, and the dashed lines are for the VIS 300 test set. Now let's look at the results in table view. The mismatched pairs are DDR trained on VIS and tested on ACL, and the DDR trained on ACL and tested on VIS. The average result is shown on the last column. We can see that DDR that are not target adapted have lowest accuracy, while models with matched or more inclusive styles are more accurate. This supports our hypothesis that style matching is important to prediction performance. Third experiment, we stress test CNNs to understand model robustness to downsampling of document training pages. We tested on 2 datasets and for all the 9 classes. Here, we reduce the number of training samples by half each time, from 50% to 6.25%. Since we only use each figure, table, algorithm, and equation once, reducing the total number of pages is roughly equivalent to reducing the unique number of training samples. From this bar chart, we see that the smaller sets of training samples decrease prediction accuracy in MAP for most cases. In general, like other applications, CNN for paper layout may have limited generalizability in that structure variations can influence the results. These seemingly minor changes alter the textures, and this challenges the CNNs to learn new data distributions. In the fourth experiment, we test the CNN sensitivity to random noise in 8 of the 9 label classes except the body text, because there's so many more body text elements than other types of elements. We don't want it to mess up the distribution. Here, we assumed a uniform label swapping of multiple classes, that is, up to 10% of a label type is changed to the remaining label types randomly with an equal chance. We increase the label noise level 2% at a time from 0 to 10%, which is considered a reasonable range for human errors. As we see from this plot, the prediction accuracy is not that much affected for most cases, though the effect was less pronounced for some categories than others. This result largely aligned with findings of Ronick in that models were reasonably robust to sampling noise. In particular, our results align well with Segal's et al.'s work in deep figures, which suggested that having more than 3% errors in their 5.5 million training labels might not affect performance much. Lastly, we evaluated the sources and distribution of the prediction errors and the rules that can help fix errors in post-processing. Some examples. Here, subsection heading is mistaken as caption, and in another case as equation. Here, bullets from body text are mistaken as equations. On the right, references are predicted as algorithms. To better understand, we made error distribution plots to show where errors come from. This plot showed the center of the elements misclassified on the normalized page, and the legend showed the ground truth type. In this case, for algorithm, about 88% of mislabeling come from text. To correct errors in post-processing, 2 heuristics are quite obvious. One is page order, i.e., there will always be an abstract on the first page with title and authors. The other is positioning heuristic. For example, the title will always appear in the top 30% of the first page. In this plot on the right, we compute the error distribution by page order, first, middle, and the last pages, and by position. We see that we can fix 9% of the false positive as they are not on first page. In short, the point is if we perform post-processing corrections, we'd be able to improve prediction accuracy at least for some label classes. In conclusion, we presented the document domain randomization method for preparing training data to extract document layout information using the deep learning techniques. The biggest advantage of DDR is that it does not require human annotation. It's fast and effective. The DDR approach, as confirmed by our experiment, can achieve competitive accuracy in extracting both graphic and semantic content. With the advantage of producing any amount of training data fastly and without human annotation, the DDR approach has the potential to accelerate the impact of CNNs on document analysis. Thank you for your time. Questions and comments, please.